Thank you all for coming. If you're here to see machine learning at scale, you're in the right place. I'm Paige Bailey, and I have a collaborator from the AZTK team, Jake Freck. We'll be giving you kind of a tag team presentation of some of the functionality of AZTK, so spinning up Spark with Batch AI, and then also leveraging some of the other tools that we have on Azure, such as Databricks. So you'll be getting kind of an overview of the machine learning process. You'll be wanting to know why you would deploy things at scale and when you would want to make that decision, and then some of the tools available for you to use. We'll also be going through a case study using transfer learning, Databricks, and distributed deep learning on Spark. So that's hopefully interesting. If it's not, I won't be offended if you flee the room to go and listen to security things in the next hall over. So thank you so much. And with that, I would like to welcome Jake on stage. And there we go.
Hi, everybody. How's it going? Like Paige Bailey said, I am Jake Freck. I am an engineer on the Azure Batch Service team, and I'm here to talk to you today about how you can run Spark on Azure with AZTK. So what is AZTK? Well, we're a supported open source Microsoft project. We're a client-side tool that provisions, configures, and manages your Spark clusters. And we're powered by the Azure Batch Service. And that gives us access to the suite of Azure Batch features, including low-priority VMs, GPU support, and the whole host of features that Azure Batch has to offer. And since Batch has no price uplift over the cost of raw VMs, you only incur costs for the time that you have your VMs allocated to your cluster. Now, in AZTK, clusters are ephemeral and on demand, which means that I can spin up a cluster in just a couple minutes. I can have the cluster live as long as it takes to do my development work or run my Spark applications, and then I can throw it away. I persist my notebooks to Azure Files. I have my data live in any of the Azure Data services, so the compute resources can come on demand. Now, we're going to switch over, do a live demo to show you just how easy it is to provision Spark clusters with AZTK. So I'm going to switch to the command line here. First thing I'm going to do is create a new cluster, give it an ID, pick our VM size, pick a number of dedicated instances, and pick a number of low priority instances. Now I'm just going to go ahead and kick this off. We'll get a digest of what the configuration of the cluster looks like. Looks like I fat-fingered something here. Let's get the VM SKU size correct. So this cluster will have 4 E32 v3 nodes. These are 32-core nodes with 256 gigs of RAM each. Now, while that's provisioning, I went ahead and spun up a cluster previous to the demo, just so we don't have to wait for this one to provision. So we're going to go ahead and interact with that. I'll SSH into the master node. This is going to give me access to all of the Spark UIs, as well as, sorry, type the ID right. This is going to give you access to all the Spark UIs that you'd be interested in seeing, as well as a suite of plugins that AZTK offers to augment and enhance your Spark experience. So now that I'm logged into the cluster, I can go ahead and start interacting with it. Can immediately start with my standard workflow. So on this cluster, I've configured Jupyter Lab, and I've mounted a notebook from an Azure file share on to the cluster. So as a data scientist, I can immediately start interacting. So we're just going to go ahead here. I'll give a brief overview of what the notebook does. So we're going to read in from the New York City taxi cab data set, and we're going to do a little data munging with Hive, create a table, select out the data we want, process it, and then plot the drop-off locations of taxi cab rides in New York over the course of a year. So go ahead here, see we have our Spark contacts up. Scroll down a little bit for you guys. Now, we are going to read in the data from Azure Data Service. We're using Azure Storage here with the WASB HDFS interface, so we can have our data hosted off the compute. So while this runs, we'll go ahead and kick the rest of this off automatically. We're converting the data how we want to the format we expect it to be in. And while this runs, we can go ahead and take a look at the typical Spark UIs that you'd see and you're accustomed to if you guys are Spark experts. So this is the Spark Master UI. We can see we have our nodes allocated and available. We have our running application. This is the Jupyter Notebook kernel. And we can check on the status of our notebook. So it looks like the data was read in successfully, and we have converted it to the format we want. We're going to do final heavy Spark step, which is converting the Spark data frame to a Pandas data frame. Go ahead and kick that off. Now we can hop back into the Spark Jobs UI, and we can take a look at our cluster's progress. You'll notice this is just vanilla Spark UI. We haven't done anything special here. We've just configured it to expose on your local machine. So this is running in the cluster, and we've port forwarded it to your machine. So you can work with it interactively like you would in a local environment, like you would in an on-prem environment. So as this runs, I'm going to pull up another plugin that we've configured for this cluster. So one thing that you might be interested in doing, in addition to developing on your notebook, is taking a look at the resource usage across your cluster. So this is a standard tick stack deployment, if you guys are familiar with that. It's built on InfluxDB with some tools to pull in data across the nodes in the cluster and then visualize it with Chronograph. So we can take a look, for example, at each of the resource usage for each of the nodes in the cluster. And if we want to, we can build our own custom dashboards as well. So let's go ahead and create a new dashboard on the fly. We can take a look at, for example, CPU usage for every node in the cluster so we can get an idea of what's going on. And let's make this bigger. So we can see that previous to our Spark job, the CPU usage was flat. But the second we started running, we can see the spikes. And we can add cells here for any of the metrics that we're interested in. You can build plugins for your own custom metrics and things like that. Again, this is just a standard tick stack deployment, which you can use for monitoring purposes. So let's drill in here to memory usage. And again, we see over the course of the application that memory usage has increased over time. So let's take a look at our Spark job, see if it's completed. All right, it looks like it has. And we can go ahead and finish off the notebook here. We're going to plot this using the data shader library. So a bit of a spoiler there. And we can see finally we come up with our graph of New York. It's a heat map. The brighter locations are based on the density of drop-offs in the city, and you get a pretty detailed view. Now, this is just a vanilla Spark program, but we can run any of our any Spark program we want using AZTK. Any of your machine learning workflows will work just as well. You can develop it interactively, and you can spin up any size of cluster you want, scale with batch. So now that that's finished, I can persist this output any way I want. Any of the Azure Data Services we can write to. AZTK comes out of the box configured to work with a wide range of services, including Azure Storage. But for now, I can go ahead and kill the SSH session. And now that I'm done using the cluster, I can go ahead and deprovision it just as quickly as I spun it up. So I'll go ahead and force this so it doesn't prompt me. Delete the cluster that we were just working on. And we can check back in on the status of the cluster that we spun up at the beginning of the demo. So we can list out our currently available clusters. And we can see that we're deallocating demo 1. We can drill in and get a closer look at demo 2, see if it's ready to be used. Oops. So it looks like it's still provisioning here. I can try and give it a second. And we can see here that we have access to each of the nodes, as well as a suite of information that we can use to take a look at the status of the cluster under the hood. So hopefully this will finish provisioning quickly, and then we can SSH in and take a look at the cluster. So just in the time that I've talked, we will be able to see that we have a 1 terabyte Spark cluster up and running, ready to be used for any of your data science workflows. And there we go. We got the master allocated now. So let's go ahead and SSH in to this cluster. Let's see, internet does not want to comply with us. Let's try and do a force refresh. Well, it looks like it's still coming up. It's taking its sweet time. But what you would be able to see is the Spark UI come up just the same as we saw previously. So we have a 1 terabyte cluster provisioned in just the time that I've been speaking with you now. And we can, here it goes. Looks like it came up. So here we got our 1 terabyte cluster provisioned, ready to go, ready for your usage. Any of your machine learning workflows will run just as easily. You have the ability to spin up test clusters at the same size that you can spin up terabytes data for your usage. So we'll hop back over to the PowerPoint. So yeah, like I said before, we're an open source project. So if you have any issues or feature requests, please reach out to us. We're interested to hear what you guys are looking for. We got our documentation hosted so you can get support and get started quickly. And if you would prefer, we have our team alias, which you can reach out to us for any questions. All right, I'm going to switch back over to Paige.
Awesome. Thank you so much, Jake. So who here is a machine learning practitioner? Who has to deal with machine learning practitioners and all of the stuff that they create? OK, so a smattering of hands both ways. Awesome. Let me hop over very quickly to my awesome. So my Spark cluster is still working. And switch over to my machine. Perfect. So as I mentioned before, we're at Microsoft Build. This is machine learning at scale. Ideally, the slide will show at some point. Is there anything special that I would need to do to get this slide deck to appear? If it's on number 7? There we go. Awesome. Or not. Let's try this. Perfect. OK. Sorry about that. So we're at Build. This is machine learning at scale. And I am Paige Bailey. I do things with computers more or less effectively sometimes. So hopefully you're all in the right place. I have about 10 years of experience working with Python, 5 building predictive models with R, and about 4 using Spark, or maybe a little bit less than 4, but it's coming up just about. I remember using Spark R, if any of you are R people. Anybody? Okay, so a couple of R people. Anybody Python? Just a few smattering of hands there as well. So if you haven't experimented with Python and R on Spark, Spark R was a horrific experience. Like, people have battle scars and war stories about trying to get it to work on their clusters. And then Sparkly R was created, and we were all very delighted. But the two primary packages that you would use to interface using those two languages are PySpark and Sparkly R. I'm based in Bellevue, which is quite close to here. And I'm a CDA, Cloud Developer Advocate, because Microsoft loves its acronyms, working on Azure and specialized in machine learning and AI. So for folks in the audience who aren't machine learning people, it's an extremely iterative process. And I'm sure if you've done a TensorFlow tutorial or something with scikit-learn, you've experienced that firsthand. So you'll start with your data scientists kind of exploring source data and attempting to understand it, attempting to understand relationships between certain features, attempting to understand distributions and kind of statistical anomalies in the data set. And then they'll begin to do something, either supervised learning, unsupervised learning, or semi-supervised learning. But the most common are supervised and unsupervised. And supervised learning, you would have two specific groups kind of in the realm of that category. So regression, which is attempting to pick a numeric value. So I expect to sell 7 widgets in July of next year, or tomorrow it will be 88 degrees, or something of that nature. And classification is trying to pick a specific type. So being able to say this is a cat versus a dog, or this is liberal, not affiliated Republican Democrat, or something. So you would go about trying to understand your data, classifying it. So that's the only way you can do supervised learning, is by having a classified data set, and then building a model based on that. So as you're exploring the data, then you would go about building and training your model. And you can do this with a variety of tools. So Python, one of the primary machine learning tools that you would have there is called scikit-learn. It gives you a wealth of algorithms, so decision trees, random forest models, logistic regression, linear regression, lots of different options for you to try. It's not a deep learning framework, but it is kind of typical machine learning, the stuff that you would expect to see in a 90s machine learning textbook. If you wanted to do deep learning, then you would probably be using something like TensorFlow or MXNet or Cognitive Toolkit or any of the other, you pick your favorite flavor sort of things. The deep learning community gives JavaScript a run for their money in terms of building out frameworks and calling them nice things and trying to get everybody to use them. But yes, and TensorFlow also has the capability to be interfaced with from a variety of languages. So there are R bindings for TensorFlow. Obviously, you can use Python, you can use Scala. They have TensorFlow.js now, so if you're a JavaScript person, you would be able to actually have node bindings interact with the GPU in your machine. But lots and lots of options for frameworks. And as you build out this model, you'll be minutely tuning different things called hyperparameters. So you'll change small modifications in specific variables and see how it impacts performance over time. So here you can see this pink line on the screen, probably not the most performant model. You ideally want to have it in the upper left-hand corner. And then as you make minute changes to your model, minute changes to your training data, then your performance goes up over time. And eventually you come up with something that is good that you want to deploy to production. But all of this is extremely interactive. There's no specific recipe or formula for getting it right the first time. And this is why interactive tools like the Jupyter Notebooks that we saw a little bit earlier today are so very, very important to the data science community, because you're constantly having to pull in data, merge it together, remove outliers, remove strange values, and then visualize distributions, visualize models, and visualize their performance curves. So your optimal model is deployed to production, and it's through either some sort of web service or encapsulated function, right? So if you, is anybody familiar with Docker containers or containers in general? Excellent. They are kind of the best practice currently for deploying machine learning models. So I worked at a place before I came to Microsoft that shall remain nameless, but it was in the oil industry. So I'm sure you can imagine. But whenever most of our data scientists would come up with a model, the final output was just a CSV file with a series of maybe IDs and then a classification. So ID and then good, and then another ID and then bad. So just going through and tagging all of the things with whatever the predicted outputs would be. It was either that or it was just some sort of static HTML business report. And neither of those things are good for production-ready work, right? Like you can't build a software application on top of a CSV. Or you can, and it would be very, very bad, right? Like that's not ideally what anybody would want to do. So the process currently is you would deploy a machine learning model, and this is usually a .py file if you're doing scikit-learn, or a .pb file, which stands for protobuf if you're doing TensorFlow. You would package it up with a schema.json file to define what your inputs and what your outputs should look like. You would have another Python script to initialize and run the model whenever it gets an HTTP request or something of that nature. And then that's what you would have. You would have this very crisp, defined entity that a software engineer can ping, just as they would ping a cognitive service in order to call the model and to get back some kind of inferencing result. And an inferencing result is just cat 75% sure, or dog 82% sure, of something of that nature. So if you've played with cognitive services at all, they're very, very cool. We saw a lot of examples of them in the keynotes a couple of days ago. But they're all deep learning models that have been packaged up in this way and are callable by REST API. So if your data scientist is building models and not packaging them up with containers or in some other sustainable manner, you should definitely have a conversation with them and kind of show them the light, because there are better ways, and if what they're creating isn't incorporated into a business process, then why do it at all, right? Like the entire idea of being a data scientist or a machine learning engineer is to provide value to a company. And if you can't take an algorithm, it doesn't matter how beautiful and great and complex it is or how accurate it is. If you can't incorporate it back into your software application, then it's useless to everyone. So your model is deployed, and then you have to retrain it. So there's a common misconception, since so very much of tutorials and quick starts on machine learning are focused on the algorithm building component or potentially the data engineering component, but they never discuss, okay, well, this assessment is right now. What happens in 3 months when the entire circumstance changes, right? Like if I was going to, so say I was building a model to predict the number of, oh gosh, I don't know, the number of Surface Books sold in Seattle during a Monday afternoon, right? That number would probably skyrocket during Microsoft conference days, right? Like during Build, it probably goes up quite a bit. During other conferences or tech conferences, it might go up. But if you were basing your model on, say, just January or just February, you wouldn't know about any of those spiky times. So you would be anticipating that the number of Surface Books sold would be quite low, when in reality, if you incorporated in, well, conference days might be an important feature, you could better anticipate those spikes. So it's the same with number of iPhones sold. On iPhone release days, the number skyrockets, but for the most part, it kind of stays stationary and might peak a little bit during holiday seasons. So you have to constantly be retraining your model, and that means you have to constantly be logging all of your accuracies. You have to be checking those predictions to make sure that they work the way that they're supposed to, and you also have to be adding additional data and making sure that it's in the same format and the same kind of sampling rate that was used to feed the original model. So it's an incredibly difficult process in order to apply DevOps practices to machine learning and to be able to, and if you don't have those, then you're not going to be able to scale effectively. So machine learning at scale on Azure, we have options. So we have ML Studio. I'm going to start with kind of the more user-friendly. You don't need to. The level of entry is very low, right? Like you're able to do a lot very quickly. Products. So you've got ML Studio, which is kind of a drag and drop machine learning environment for building out models. It's based on TLC, which has now been rebranded as ML.NET. So all you would have to do to implement a model is drag in data, apply an algorithm, and then it would give you back kind of a friendly REST interface that you can then use however you want, just like a cognitive service. We also have cognitive services, which are leveraging deep learning, specifically transfer learning, to do a number of things. So vision, speech, text, lots of different functionality. And all of that does count technically as deploying machine learning at scale. They're very scalable solutions on both ends. You can set them up as serverless functions, and that makes it very easy to kind of incorporate them into a more traditional Kubernetes type environment. And then also we have the ability to use Spark for distributed deep learning and distributed machine learning, either with CPUs or with GPUs, which is very exciting. So we saw AZTK talking about batch. We also have something called Databricks, and we'll be diving into that in a few minutes. So this is just kind of a process flow for the machine learning at scale options that you have on Azure. It's not quite complete. The Azure Machine Learning environment includes everything from Azure Notebooks to Jupyter Hub installations to the data science virtual machines and the deep learning virtual machines. And as you go about incorporating data, training, creating your model, and then deploying with either some sort of container service or our Kubernetes service, that's kind of the process flow that you would go to. You also have the ability to do machine learning directly on top of SQL Server. So that would be with Python or with R, and it wouldn't be deep learning. So things, again, like deep neural nets, you've probably heard buzzwords, TensorFlow and Cognitive Toolkit and such. But it would be more things like building out decision trees, building out, building out random forests, and logistic regression in those toolkits. And then that's kind of an overview of the data science life cycle. It's not perfect, but it goes through the process of you have a question that you want to answer that would provide your business with some value. You acquire data that you think will help you understand that question, and you spend a lot of time cleaning it, getting it into this nice, friendly rectangular format, building out your data pipelines and defining sources and data dictionaries, and then applying the modeling steps, so doing things like feature engineering, training your model, selecting a model, trying a different one and seeing how that impacts performance, evaluating it, defining what metrics that you want to capture. Like, is it accuracy or is it something like an F statistic? So for example, if you had a data set where you were trying to figure out which pictures were cancerous, which x-rays had tumors, it might be that 99% of them are okay and there's 1% that are diseased. But if that was the case and you were just after accuracy, if you built a model that just said everybody was fine, you would have 99 predictive accuracy, which is great, but it's not really answering your question. So you need to think about other ways to incorporate things like precision and recall and an F statistic to understand your data a little bit better. And then you would deploy it as a model, and again, make sure that you keep monitoring your accuracies, you keep checking, and that you keep refreshing it with data sets and potentially even retraining models with different hyperparameters. So that's the data science lifecycle best practice. There's a great paper, if anybody's down with reading academic papers, called the TensorFlow Extended paper. It was published by Google in 2017, so it's very, very new, about halfway through last year. and it focuses very technically on all of the different steps that you have in this process. And this is actually my favorite viewpoint of how you would go about operationalizing a machine learning system. You have to be able to understand logging and data validation, and being able to understand how the methodology that you use to serve a model, to deploy it, to have a nice, friendly endpoint for software developers or whoever to connect to, impacts some of the choices that you need to make. So challenges. I've probably been talking all morning about challenges, but some of the biggest ones are that you typically need a lot of data to train a model, especially for deep learning models. And you need to prepare the big data sets before you can even begin training it. They have to be into a nice, friendly, rectangular format. Most deep learning and machine learning models don't like dealing with null values or with NAs. Obviously, your model's only going to be as good as the data that you put into it. So you have to be able to prepare everything very quickly, even for these massive data sets. And that's where clusters, especially Spark clusters, can come in very handy. And the model training phase usually has to access those large data sources. Also, you might end up with a use case where if the number of users who were being incorporated into your model was very small at the beginning, but then suddenly your startup, surged in popularity, which is great. But not so great if you don't have the infrastructure to take care of it. If you wanted to retrain your model, maybe CPUs were no longer effective. It takes hours instead of minutes to train. And you might want to be able to scale up with GPU-enabled machines or a larger CPU-enabled cluster. And you want to be able to make all of those decisions automated as opposed to having something break and then you have to hurry up to fix it. So what is Apache Spark? I feel like we've been talking about it all morning. So for folks who haven't had experience with it yet, here's what it is. So it's an open source cluster computing framework out of UC Berkeley, specifically the AMP lab. It supports batch and streaming data sources and a whole bunch of languages. So R, Python, SQL, Java, and Scala. And there are always projects kind of focused on incorporating new interfaces to those languages. And it can run run workloads up to 100 times faster. So if you remember, there was a conference a couple of years back called Strata Hadoop that was funded by O'Reilly and Cloudera. They've recently removed the Hadoop from the name of the conference because it's no longer in vogue to talk about Hadoop, since Spark is so much more widely used in industry and so much more effective and so much speedier. And friendly to use and more straightforward. And I can't say enough nice things about it because it's awesome, and you should all go try it out. And you can see that a lot comes in the box with Spark. So you get Spark Streaming for streaming data. We saw a demo of that the first day with Cosmos DB. You get Spark SQL for querying. You get GraphX, and you also get this thing called MLlib. And MLlib is machine learning on top of Apache Spark, but in a very straightforward manner. And what do I mean by that? So it's a sub-project that provides machine learning primitives. It was, again, created by the folks at AMP Lab. They're awesome. And it's been shipped with Spark since version 0.8. So it's been around for a while. It's pretty robust, and it's production-worthy. And it's comparable or even better than other libraries specialized in large-scale machine learning. The syntax is also really, really friendly. So for very specialized machine learning algorithms, so logistic regression, naive Bayes, generalized linear regression, clustering, especially k-means clustering, decomposition and collaborative filtering, like alternating least squares, it's really, really useful to use, and the syntax looks almost exactly like scikit-learn syntax. So the current methodology for data science is you have some lady or dude working at a computer, usually a kind of an isolated desktop environment. And this is by no means best practices, right? Like this is kind of, everybody should have little light bulbs flaring in their heads, like why are they working in a local environment? Why don't they have version control? Sort of things. But it's usually one person working on a desktop, pulling in data from a variety of sources, doing a lot of like very bespoke data cleaning, so trying to get it into a correct format that they can actually use a machine learning algorithm on, deploying it on this much, much smaller than production data set, training it, testing it, and then saying like, okay, well, let's try it. We've tried it on 1,000 records, and we're getting great performance. Let's try it now on 1.5 million records, and hopefully it still works. And then you kind of monitor progress over time. But that's not ideal, right? Ideally, you would want to be able to sample a larger portion of your data to base your model on. You would want to be able to kind of do data cleaning processes at scale, as opposed to just very one-off situations. And MLlib helps a lot with the machine learning aspect of that, and Spark helps a lot with the distributed nature of those requests. So why use MLlib? Scalability, performance, user-friendliness. It looks just like scikit-learn, and it integrates with all of the other Spark components. This is what I see used most often in industry, because machine learning algorithms are very easy to inspect. You can understand what's happening with them, whereas for deep learning algorithms, it's much more difficult to understand the nuances of what's happening in deep neural networks. So some options that you have for deep learning. There's Dist-Keras, which is an open source framework for distributed training of Keras models. Keras is the friendly developer-facing front end for Theano, CNTK, and TensorFlow. And it also leverages Apache Spark and runs on Spark data frames. So that is an option, and that's available with Databricks kind of out of the box. There's also this thing called Spark Deep Learning. And that's the use case that we're going to see today. So let me bounce out of the presentation because I hate slides, and go to the notebook that I have provisioned in Azure. So this is something called transfer learning using Spark Deep Learning. And I want to show you the transfer learning tutorial that it's based on. So let me head over to TensorFlow's website. Transfer learning example. So this is retraining a model that's already been built to detect different kinds of flowers. So transfer learning is awesome because you're capable of taking a model that was built by Google or Facebook or Amazon or Microsoft or somebody with a lot of compute capacity, a lot of data, and a lot of time. They built out this great thing over the course of weeks, maybe even a month of training, and millions of images. And you can use it and all of the knowledge that it's gained very quickly. So instead of you having to build a model to detect flowers and having it take weeks or months, you can build on top of this guy, and it takes like maybe 6 minutes to create a new model. And you can also train based on just the primitives that it learned. So I built a transfer model just recently that detected different clothing styles. And it took 6 minutes to train and was something like 98% accurate. But that was because I was building off a model called Inception. But the idea behind this transfer learning tutorial is that you bring in some pictures of flowers, so daisies, sunflowers, dandelions, roses, sunflowers, and tulips. And then you kind of train on these images. You do a lot of training steps. You do some hyperparameters. And since it's a tutorial about TensorFlow, it's very verbose. There's a lot of words here. This is also focused on doing it locally on a GPU-enabled machine or on a CPU-enabled machine. But for CPU, it takes 30 minutes to do, and for GPU-enabled, it usually takes about 4. This is doing the same exact thing, except taking that model and doing a distributed transfer learning project, implementing it on Spark with just a GPU-enabled cluster with 4 nodes. So as I go through, I can click Shift-Enter. It runs the commands, sends them to the cluster. And this is kind of, for folks who haven't had experience playing with Spark before, this is another very friendly interface to Spark itself. You have the ability to do auto-scaling through this user interface. You can specify the number of workers that you want, kind of the configuration of the environments, so standard all the way up to pretty sizable clusters. You can add models and libraries very easily. So this is something that I love. If you want to attach a specific library to your cluster, instead of you having to manually going about and installing that library onto every single one, you just attach it to your cluster here, and it's good to go. And Databricks also keeps a version of every single Python library associated in PyPy, so you don't have to worry about versions yourself. So this has several libraries attached. You can see the notebook that I have here. It's very easy to attach to different clusters if you wanted, to restart clusters, and to spin them up. So just think of this as kind of an optimized, very GUI interface to what you just saw with Batch. And it also enables auto-scaling and integrations with some other things. So we have the directories for the daisies. We're putting them in more permanent storage so that I can analyze them. And we're doing a small set for demonstrations here. So here you can see the different images that I'm pulling in, their names and their sizes, just kind of an inspection. We can load images and then apply transfer learning to it. So the model itself is just this, right? So from PySpark, import these different functions, and then apply image schemas and train the classifier with this. So it actually takes more lines of code to get the data into the state that it should be than to run the model itself. This is all it takes to run. So this Inception v3 model, it's built on top of 14 million images and takes I think a week to train. And to train it on this with my Spark jobs, it is not very time intensive at all. So you can see it took 2.70 minutes rather than a week. And then if you want to see how you did, you can spin up the labels and the confidence levels associated with each. And I think I only have 10 displayed here, but let's try with like 40. Oh, there you go. So the reason that it's not running is because I haven't run the cells up here. And as you can see, you can just kind of cycle through and submit commands to clusters for execution, and then see how it performs over time. So one of the things that is not quite as straightforward to use in Databricks in this portal environment is something called TensorBoard. And TensorBoard, I mentioned before that neural networks are very difficult to kind of inspect, to understand what's happening. If I log into a virtual machine, I'm pretty sure that I have TensorBoard up and running. So we'll see if I can show you a real live example. This is an X2Go client that specifically, that it's fixed towards one of my deep learning virtual machines. You can see that there are a number here off on the right. And ideally it would pop up with a user interface. But it looks like it's taking some time. So just for that, I'm gonna head back to the slide deck and talk a little bit about Kubeflow because we're nearing time. So Kubeflow is specifically focused on doing painless machine learning deployments on top of Kubernetes. So this, once you've created a model, once it's in a container, once the requirements have been defined for the compute capacity, you would want to be able to deploy it in a distributed manner and automatically scale based on the number of users pinging the service, the number of pieces of data that have to be incorporated back into the model, and Kubernetes is excellent for that. So I was asked yesterday if I think that there's a library that's not getting enough love. What is it, and how can I get involved? And the answer would be Kubeflow. It is fantastic, and if you have any passion around machine learning or Kubernetes, I would strongly suggest taking a look at it. So that is the end of the presentation. I want to be respectful of everyone's time and respectful of everyone's need for lunch. So if you have any questions, please feel free to ask. But otherwise, thank you so much.